Good morning, everyone. We are starting our CMSA Colloquium. Today, we are delighted to have Mykhaylo Shkolnikov as our speaker. Mykhaylo is based in Princeton, where he is a professor at the Operations Research and Financial Engineering Department. Prior to that, he was in California, where he completed a PhD in math at Stanford, and he's also spent some time as a postdoctoral scholar at Berkeley. Mykhaylo's work focuses on probability theory and partial differential equations. For his contributions on particle systems interacting through their ranks, Misha received the Erlang Prize by the Applied Probability Society. Today's talk will be about a probabilistic approach to free boundary problems and its application in finance and neuroscience. If you have any questions, please feel free to ask. Misha doesn't mind. Okay, the floor is yours, Misha.
All right, thanks a lot, Sergey. So it's a pleasure to be with all of you, at least virtually. And, you know, as always in this virtual environment, I very much encourage you to switch on the video. So it would be a pleasure to see many of you in front of me. So please do if you like. And also, you know, as Sergey said, so please feel free to just speak up and ask questions if you want to ask something. All right, so my talk will be about a new notion of solution that we have introduced for free boundary problems, especially for singular free boundary problems. And basically, I want to make an argument for why this new notion of solution is useful. And you know, this argument will be twofold, to put it in a nutshell. So on the one hand, I'll try to convince you that these probabilistic solutions naturally appear when you study large interacting particle systems, in particular ones that show up in applications. And secondly, this notion of probabilistic solution sits in between weak and classical solutions. And I will try to argue that it's sort of the right notion to be weak enough to give you existence, but at the same time strong enough to give you uniqueness of solutions. So somehow you can develop a well-posed theory for various singular free boundary problems using this new notion. Now, all of this is joint work with various people who are listed here, so mostly with Sergey Nadtochiy, and you know, some of the papers also joined with Francois Delarue, Jiacheng, Zhang, and Xiling, Zhang. And so what I will do today is to explain this approach in a particular example to kind of give you an overview of how this program works. So it's much more general, and I'll comment on that in the end. But for the talk today, we will look at kind of one particular free boundary problem and how probabilistic solutions arise for that. You know, I will talk about the interacting particle systems, where they come from, and the applications in finance. Okay, so this will be sort of one case study, but keep in mind that what I'm about to say is actually much more general and applicable to many other free boundary problems as well. Okay, so the plan for the talk is to start with the applications, specifically with an interacting particle system that shows up when you study systemic risk in finance. And then, you know, I will use that sort of as an applied motivation to study the large limit, the large system limit for this particle system. And this will naturally lead us to this concept of probabilistic solutions, which will be sort of the key player in the talk. And then, you know, we will come back a little bit to the applications. I'll explain what the mathematical analysis means for those. And then at the end, try to explain the scope of this theory beyond this one example case that I will discuss today. All right, so let me start with this interacting particle system coming from systemic risk. So first, let me say just a few words what systemic risk is about. So it's an area in finance and mathematical finance that has been very active, especially after the financial crisis of 2008 and 2009. And the goal was to understand essentially how defaults of bankruptcies can propagate through a financial network, right? And so this is a kind of question which shows up, in fact, in various applied areas where more generally you can think about a network and you are trying to answer the question how local effects in this network can propagate to create something on the macroscopic scale. So another interesting example would be, comes up in neuroscience, where people are interested in synchronization of neurons. So a phenomenon where somehow a few neurons spike in the brain, but this leads to spiking of a significant number of neurons known as synchronization, and that's related to many of our cognitive functions and such as motoric response and things like that. Okay, but coming back to finance, so again, to stick to one example and be more specific, in the systemic risk setting, you imagine that you have a financial system. So for concreteness, just think about some number of banks that borrow and lend to and from each other. And we will be interested in the situation where the system will be in distress, meaning that one or several of these banks will default, so they will declare bankruptcy, which will lead to losses to their counterparties because they cannot repay their loans. And so these losses, if they're severe enough, will lead to the bankruptcy of the counterparties and could potentially propagate through the whole system, right? So that's the type of setting that people are interested in. And again, what we want to understand is how some sort of local effects, so the bankruptcy of some, say, local retail banks can propagate and, maybe create a crisis, for the whole system throughout this banking network. Okay, so to study something like this, there is sort of a typical class of models that usually go by the name structural models for systemic risk. And I'll pick kind of the simplest toy model that you can imagine from this class to keep things kind of manageable for the talk, but really, again, think of it as some sort of backbone model, which on top of which you can build and make things, more realistic and build more detailed models. Okay, so the simplest way to think about this interconnected banking system and the default cascades is the following. So imagine you have capital N banks in your system. And so I'll start with the asset values at time 0, which I will call x1 0 through xn 0, right? So imagine initially the asset values of all these banks on the positive half line. So they're all solvent and have, some positive amount of assets to start with. And now these asset values will evolve in time, and I will choose the simplest dynamics imaginable. Namely, I will let those asset values just evolve as independent Brownian motions with some drift coefficient alpha and some dispersion coefficient sigma, both constant. So what this corresponds to in finance is you imagine that these banks are investing in the stock market and possibly in the real economy. And so they're making some sort of return, which is captured by the alpha. And there is some uncertainty or risk involved, so that there is some dispersion or some noise, if you like, which is quantified by this coefficient sigma. Okay, so it's really kind of the simplest imaginable dynamics that you can go with. And so something interesting will happen in this model only when banks actually default, which is modeled by the fact that the asset value process hits zero. So when it hits zero, we kind of imagine that the corresponding bank ran out of assets, in which case we will declare it bankrupt and we'll take it out of the system. And in this case, something interesting will happen, namely, since we're assuming that banks are interconnected through the borrowing and lending, this default will create losses to everybody else, which mathematically will mean that our processes, our X processes for the other banks will make downward jumps that will be parameterized by parameter C. So financially or economically, this parameter stands for what people call non-core exposure. So basically, the higher this parameter will be, the more linked our system is. And so the more severe the losses will be when one of the banks defaults. Okay, and so there is exactly one interesting feature in this model, which is by design, because we want to focus on exactly that. And this feature are the default cascades. So you can imagine a situation where one of the processes reaches zero, so the corresponding bank defaults, it creates losses to everybody else. So the other particles are shifted down by this amount, by some positive amount. And this could force additional particles across zero instantaneously, meaning that instantaneously, in addition to this one original bank, some additional number of banks will default, in which case that will create additional losses to the rest of the system. And so we will move our processes down further, which could create new defaults and so on and so forth. So in this model, you can have kind of a toy version of a default cascade that you do experience in practice, and which to some extent actually happened in the financial crisis in 08, 09. All right, so this is a description in words. Let me jump more into the mathematics of it. So as I mentioned, I will write x1 through xn for the asset values of my banks. And I will mostly use the terminology from interacting particle systems. So I will speak of particles when I refer to those processes. And so as long as these particles are on the positive half line, again, they will move in the simplest possible way, namely they will just follow independent Brownian motions, BI, with these two coefficients, alpha and sigma, standing for the drift and the dispersion. And so something interesting will happen only if one of these processes crosses zero. And so therefore, I introduce these heating times tau that you see at the bottom of the slide. So these are the first times a particle crosses zero. So in other words, the times of default of bankruptcy for the bank I. And so when a particle hits zero, as I mentioned, it will be removed, and its effect on the rest of the system is the following. So I will just shift the remaining particles by a constant amount to keep things simple here. And this constant amount, I will choose to be this ratio of C over M. So again, the idea is that this ratio should be large when C is large. So if you have a strongly connected network, if there is a lot of borrowing and lending, C is large, and so this quantity will be large, and so the losses will be large. And it's a decreasing quantity in N, so if you have somehow more shoulders to shoulder the burden, then the losses to every single entity will be smaller. So that's the idea here. Okay, so again, think of this just as a toy model. One can make it more realistic by choosing more complicated functions of C and N, but this will be particularly convenient for our talk here. All right, so our particle I has disappeared. We have shifted everybody else. And as just mentioned, of course, there can be now some additional K particles indexed by I1 through IK, which will cross zero because they're shifted down by this positive amount. And so if that's the case, we take them out. So all of these banks are also removed from the system. And we change the shift from the ratio C over N to C over N times K plus 1 to reflect that K plus 1 banks now went out of business and not just one of them. Okay, so we keep things extremely simple here and make the losses just proportional to the number of banks that went out of business, right? But nonetheless, even in the simple model, you can have this cascade effect that you start with one bank defaulting. Because of the losses, you have these K additional defaults. Those create additional losses, which can lead to more defaults, and so on and so forth. So in principle, this one default could lead to the collapse of the whole system with non-zero probability. All right, so that's the model. In terms of formulas, let me just quickly translate what I said into the last equation on the slide. So if you look directly at the last equation, so the asset value of any given bank will move as a Brownian motion with drift in this model. And then this last term, the sum, corresponds to the cumulative losses a bank incurs. So du is the number of defaults at time u. And so you can quickly convince yourself that my description from before means that by time t, you just count how many banks have defaulted, and you multiply this number with C over n, and that's the total loss that a given bank I will incur by time t. All right, so maybe I'll quickly stop. Are there any questions about the model before I jump into its analysis? All right, if not, then let me move ahead. So, right, so we have this interacting particle system, and both for mathematical reasons and for application reasons and finance, we will be interested in the limit of this system as n goes to infinity, right? So from the financial point of view, the reason to look at this limit is to study precisely the macroscopic default cascades. So we want to understand, under which circumstances a big fraction or a non-trivial fraction of the system defaults, and to make the meaning of non-trivial fraction precise, we will take n to be large, and a non-trivial fraction will mean an order of n entities going bankrupt at the same time or in a short interval of time. All right, so that's what in finance you refer to as a systemic crisis, typically. Okay, and so what I want to explain is how this n to infinity limit will lead us to a free boundary problem, and more specifically to this new notion of solution called probabilistic solution of a free boundary problem. Okay, so to get there, the crucial observation is the third line from the bottom on the slide, right? So somehow the only non-trivial term in my dynamics is the term due to the losses, right? That's the one that captures the cascades. And so the main observation to pass to the limit is this little equation that you see in the third last line. So the total amount of loss that the bank incurs can be rewritten as the sum of indicators. So what does it do? It just counts the number of banks that go out of business by time t. And so I take that number, that this is the sum over j, I multiply with c over n, and that's the total loss that my bank will have by time t. Okay, so why is this? Why is it useful to rewrite the interaction term like that? Well, that's because we see that the interaction term is an empirical average, right? And that's a class. So therefore, our particle system falls into a class that's very well known, and particularly in mathematical physics, or generally in physics. And so what we have here is a particle system with mean field, so-called mean field interaction, right? So that statement corresponds just to the fact that the interaction term can be encoded in terms of some kind of empirical average, as you see in this third last line here. All right, and so there is a very well-known heuristics, which at least in the mathematical literature goes back to McKean and Vlasov, and known as mean field or McKean-Vlasov heuristics, which tells you that whenever you have this kind of interaction, whenever you have interactions through the mean field, there is a way to guess the behavior as n becomes large. So basically, there is a way to guess how a representative bank or a representative particle in our system will behave when the system becomes large. And so here it goes. I'll explain it not for our system initially, but for a more classical system with mean field interactions. So that's the first equation you see on the slide here. So in this equation, I look at the slightly different dynamics of particles where the interaction is more smooth, namely where the drifts and the diffusion coefficients of the particles are some nice, things, say smooth C infinity functions of the particle locations themselves and the empirical measure rho and s, right? So this empirical measure is just a measure which puts mass of 1 over n at the n locations of my particles, right? And so in particular, my empirical average from the previous slide is just an integral of some test function with respect to this empirical measure. So whenever you're in this kind of situation, so whenever you feel the presence of the other particles only through the empirical measure, there is the following heuristic to pass to the large n limit. Namely, you say, well, suppose we already knew there is a limit, rho, to my empirical measures, right? So to my empirical measures of the particle locations. If that's the case, then at least for large values of n, I can replace rho n in my dynamics by this limit rho, right? And the error I will make should not be too large, because if rho n goes to rho, the two will be close for large n. All right. So if I replace rho n by rho, I arrive at the equation for x bar I in the middle of the slide. And now you see that there is a decoupling phenomenon happening here, right? So once rho n is replaced by rho, the particles no longer interact. In other words, the dynamics of particle I just depends on particle I itself, and rho is just some deterministic quantity. So I have now a system of n independent particles, and then of course we know, everything you could possibly want to know. So in particular, we know that the empirical measure of this new system of the x bars will converge, and it will converge to the law of one particle trajectory, say x bar 1. Okay, so this follows from classical results like Sannov's theorem or Varadarayan's theorem in probability. All right, and so if you plug this back in, you arrive at the last equation on the slide. And so, the conclusion of this heuristic is that a typical particle, so a representative bank, let's say in our context, will behave in the large system limit according to a diffusion equation, which is nonlinear in the sense that the coefficients B and sigma depend on the law of the solution itself. Right? It's called nonlinear because if you write the forward Kolmogorov equation for corresponding to this last equation, it will be nonlinear rather than linear. All right, so that's a general heuristic. I can apply it to my setting, right? And so in my setting, I will arrive at the first two equations on the slide, right? So it will tell me that a representative bank will behave as a Brownian motion with drift minus some loss process lambda. And this loss process lambda is somehow the result of that empirical average that we had originally before we passed to the limit. And so the limit of this empirical average will be just the corresponding expectation, which, is an expectation of an indicator becomes a probability here, right? So in other words, we arrive at the following problem, right? So you have some initial value x0 bar. So it describes the initial state of the systems, so the initial asset values of the system. And we're trying to find a function lambda such that if you run a Brownian motion started from x bar and you subtract lambda, the probability the resulting process will hit 0 by time t, so the probability of default, should be equal to lambda itself up to this proportionality constant c. Okay, so you can think of it as sort of a fixed point problem, right? So we're looking for a choice of lambda, which will kind of close this fixed point loop, meaning it will lead to an x bar whose default probability or hitting probability is precisely lambda itself. Okay, and so it turns out that this limiting problem that we very naturally arrived at can be viewed as a probabilistic formulation of a very well-known free boundary problem, which goes by the name one-phase supercooled Stefan problem. So let me first formalize that, and then I'll talk a little bit about this free boundary problem that shows up here, right? So the formal theorem, from going back to first paper in this line of work with Sergey Nadtochiy, says that if you start with asset values x0i and the empirical measure converges to some limit, call it nu. If this limiting measure is nice, if it has a density with nice properties, then we can prove that the empirical measure of the asset value trajectories, which describes everything in your system, the whole dynamics of the system, will converge at least along subsequences. That's the meaning of the word tight in the theorem. And the limit points, so the limits of the various subsequences, will give you solutions of the problem that you see here on the previous slide, right? Of this x bar lambda problem in the first half of the slide. All right. So, okay, now I want to explain that this problem we arrive at is actually a very well-known problem called supercooled Stefan problem, just recast in a new light. And so, yeah, let me explain that. So let me simplify things even further and set alpha to 0 and sigma to 1, so to make the ideas as clear as possible. So in this case, we are just looking for a function lambda, so that if you run a standard Brownian motion and you subtract lambda, the probability for this process to hit 0 becomes equal to lambda itself. All right, so if imagine you have a solution lambda of this problem, and imagine it's smooth. So at least in the sense that lambda prime exists, so the derivative of lambda exists. So if that's the case, then you can write a forward Kolmogorov equation, PD, for the densities of the process X bar. And so this PD is the equation for the unknown little p in the third line from the bottom, right? So the densities of a solution X bar will evolve according to the heat equation. So that's the first part of the PD. And then there is a first order term, which will involve the lambda prime, the derivative of lambda. Okay. On top of that, I can recast the fixed point condition in analytic terms. So it's easy to convince oneself that, lambda being equal to the absorption probability means just that lambda prime equals up to a proportionality constant to the derivative of P, of the density of my process at 0. Okay, and so, the problem above in PD terms becomes the problem below for the unknowns P and lambda. And on top of that, I can make a quick change of variables from P to U, where I look at my space variable X relative to lambda, right? So I'm basically plotting lambda, so the cumulative losses I have up to a given time t, and I change the space variable to live above the graph of lambda. So, these are asset values that are sufficient to survive up to a given time. All right, so making this change of variables, the PD transforms, and of course, it's easy to do this computation. So you get a new PD for the function u, and this new PD is that famous free boundary problem that I alluded to before, known as a supercooled Stefan problem. So, rather than going through the equations, let me describe what this problem actually means, right? So the Stefan problems in general were designed to model freezing of liquids. And so here in this particular case, U stands for the temperature in the liquid at time t and at the space location little x. And so, and the PD itself just stands for the statement that the temperature changes according to the heat equation. So heat diffuses through your liquid. The boundary condition, so this equation which connects lambda prime to the derivative of u in this physical context, stands for the fact that you are transforming, so your liquid is freezing, right? And so the energy needed to freeze additional parts of your liquid comes from the gradient of the temperature next to the boundary. Okay, so this this leads to a certain conservation of energy in the system, which I will not describe in too much detail. And then you have boundary conditions. So you start your liquid from some initial temperature F, and the last condition, the fact that U is equal to 0 at the boundary, stands for the fact that you assume that freezing always occurs at the equilibrium freezing temperature that we set to 0 here. All right, so I'll say more about the history of this problem and what is known about it. But before that, I'll show you a quick video of the actual phenomenon this problem describes. So let me stop sharing the slides for a second and instead share the video. Okay, so here it goes. So what you will see will be, freezing of a liquid, namely of water. But the interesting aspect in the video will be that we will take supercooled water. So we will take water which is cooled below 0 Celsius, but under conditions which will still remain liquid. And so in the video, this water cooled below 0 degrees Celsius will be poured into a glass, and you will see how it freezes. So here we go. Right, so I guess the keyword here in this video is the real time, right? So, the interesting aspect of this process is that, when you take a supercooled liquid, so liquid cooled below its equilibrium freezing temperature, and it starts to freeze, this freezing tends to happen extremely quickly. So you can see it with your naked eye, whereas, that would be atypical for a normal liquid, so a liquid that's above the freezing temperature initially. And so mathematically, this very fast freezing translates into singularities or blowups, which make the mathematical analysis interesting and more difficult. So specifically, what you should think of in terms of this problem for U and lambda is the following. So you saw the eyes moving kind of from right to left in the video. So think of lambda as describing the location of the interface between the ice and the water. So starting at 0, say, and increasing as it goes from right to left in the video. So that's the lambda, and U is the temperature, again, in terms of the horizontal coordinate, it's the temperature of the water, the remaining water in the glass at time t, and different positions, little x, where x again is the horizontal coordinate. And so this fast freezing that you saw in the video corresponds mathematically to a blowup of lambda prime, right? So lambda prime stands for the velocity, the speed at which the interface was advancing. And so if I have a time point, capital T, at which lambda prime blows up, so goes to infinity, it corresponds precisely to a situation where my interface is advancing at infinite speed for this one instant. And that somehow captures, at least to some extent, this physical phenomenon that you saw, this very fast freezing of a supercooled liquid. All right, so I had kind of a history lesson on Stefan problems prepared here, but let me skip it to save some time. Basically, the point is these free boundary problems for this unknown boundary lambda have received a lot of attention, but mostly from the PDE or analysis point of view. And so, basically 2 types of solutions have been proposed, so-called weak solutions in the PDE sense and classical solutions. And so in the case where the liquid is supercooled, you cannot work with classical solutions because of these blobs in lambda prime, which make it impossible to pose the boundary condition classically. And so therefore, people have looked at the weak formulation of these free boundary problems and its generalizations. But the issue with that is that you typically lose uniqueness when you go to the weak formulation, right? So you kind of relax the formulation of the PDE. This will give you existence of solutions, but you typically lose uniqueness. And so what I want to argue, and that's the main mathematical point of my talk, is that the probabilistic formulation or the probabilistic notion of solution that we naturally arrived at actually gives you a notion of solution which will give you both existence and uniqueness. And so it sits somehow right in the middle between the classical and the weak formulation. Okay, so let me come back to that. So at the top of the slide, I wrote again the probabilistic formulation of this free boundary problem, right? So quick reminder, right? We're looking for a function lambda, so that if I subtract it from a Brownian motion, the heating time distribution will give me back my function lambda. All right, so, the first surprise here, which goes even beyond the blow-up statement that I wrote down before, is that you have non-existence for this problem in the space of continuous functions. So that's really surprising because your input is a Brownian motion, right? That's a continuous process. But what I'm claiming here is that you can prove that for certain, perfectly nice initial conditions, there won't be a solution. So there won't be a solution capital lambda that is continuous, right? So in particular, one example is when the expectation of the initial value is too small. So if it's smaller than 1 over 2c, so the initial condition can still be perfectly nice, right? So it can be compactly supported, have as many derivatives as you want, but if it satisfies this inequality for its expectation, you can prove that there won't be a continuous solution to this problem. Okay, so in fact, not only the derivative of lambda can become infinite, but lambda itself could have a jump. And so to accommodate for that, we move from the space continuous functions to the Skorohod space of functions that are right continuous with left limits, right? So we allow for jumps, in other words. And, that's yet another argument to work with these probabilistic notions of solution, because, this the Skorohod space that, is very well known in probability has, many nice properties that you can exploit to study solutions. All right, so we allow for jumps to ensure we have existence, but then we run immediately into the next problem, namely there is non-uniqueness, right? So you can also, again, quickly convince yourself that in the space where you allow for jumps, you can now construct multiple solutions to the problem with the same initial condition. Okay, so somehow you would like to know which one of those is the actual physical solution, the one which actually describes the freezing process, or that actually describes the large system limit of my interacting particle system. And so if you think more about this issue, what you realize is that the probability of absorption, which features in the problem, or its pre-limit counterpart, the empirical average of the heating times, both of these do not really specify the cascades, right? So it's most easily seen on the interacting particle system, right? So when I defined it, I had the additional feature that I formed the cascades from the bottom up, right? So I started with the particle that actually has hit 0. Then I looked kind of at the weakest banks, so the ones with the smallest asset values, figured out which one of those default due to the losses, and then I kept going kind of from the bottom to the top of my system, right? And so in particular, this corresponds to a certain minimality property, right? That I choose somehow the smallest cascade, so I absorb the smallest number of particles that allows the rest of the system to survive. And so the correct solution of the limiting problem, the one which will give me the large system limit, should inherit this minimality property. So that's encoded by the last few equations on the slide, but you don't have to read them too carefully. So basically, they just formalize the statement that in the limit, I also want to remove the smallest fraction of my system, so the smallest portion of my distribution, which will allow the rest to stay above 0. So that's this infimum, what this infimum at the bottom of the slide stands for. And so once you enforce this minimality, you get now a notion of solution which has a chance to be unique. And it turns out it is, right? So with this additional minimality condition, you do get well-posedness of the probabilistic formulation of a free boundary problem. And so you get kind of all the desired things, right? You got both existence and uniqueness. And from that, you get the fact that this unique solution is the limit of the full sequence of interacting particle systems that we discussed before. All right, so let me explain this in a little bit more detail, right? So when you look into the limiting problem, it turns out there are three regimes which also translate nicely to the financial meaning of this whole thing. So let me explain these regimes. So the first one is the regular regime, where things are well behaved, so your system is not really in distress. So if you look at the equation in the middle of the slide, what it is saying is that if I look at QTX, so that's the density of X bar T minus, okay? So the way you should think about it, we're looking at some particular time point, little t, and we'll look at the behavior of our financial system or interacting particle system, if you like, right before this time point. So t minus corresponds to the left limit of the X bar process, right? And so you're kind of right before a potential cascade, and you want to know, okay, are you on the verge of a huge default cascade or a systemic crisis or not, right? So, or mathematically, you want to know, will a jump happen in the function lambda at time t or not? And it turns out that if you look at the distribution right before time t, or specifically at the corresponding density q, whether or not you will see a jump depends on how q will behave near zero, so near your absorbing boundary or your free boundary. And so in this nice regular regime, this q is small near the boundary, right? So what this lim sup inequality encodes is, on the one hand, that q tends to zero at the boundary, so it's small in that sense, and it even goes to zero linearly, right? So it can be bounded by some constant times x near the boundary. So if that's the case, then everything is all right. So you will not see a jump. So lambda will be smooth, meaning you can show that on at least on some little time interval beyond time t, it will be continuously differentiable. So if your pre-t density is nice, you don't have a jump, you get a continuously differentiable free boundary locally in time. Okay, and so in particular, on this little time interval, you could have even used the classical formulation of the free boundary problem, and your solution will be, in fact, a classical solution in the PDE sense. So that's kind of the classical or the regular regime. The second regime is kind of the other extreme, which I called here the jump regime. So if so here you should look at the equation, at the inequality involving Q in the third line, right? So what it means, if you think about it, so morally speaking, what it means is that the limit of Q of the density at the free boundary actually is now positive, and it exceeds the threshold of 1/c, right? So it's positive and large enough. And if that's the case, you have somehow, either a lot of banks near this default threshold, or in the physical context, you have a liquid that's relatively far below its equilibrium freezing temperature next to the ice. And so this will allow the ice to advance very quickly, or in the financial context, it will lead to a systemic crisis. So you will indeed see a jump here, and you can write down the formula for the size of the jump. So how severe the systemic crisis, or how far the ice will advance instantaneously in this situation. Okay, and so on top of that, you can show that on a little time interval beyond t, lambda will be again continuously differentiable. So it will jump, but after the jump, you will have a little time interval on which, again, the classical formulation will hold and nothing, irregular will happen. All right. So these are the two extremes. And then there is an intermediate regime, which I called here mildly singular for the lack of a better name. So again, look at the second line at the inequality for Q. So remember, 1 over C was this critical threshold above which we saw a jump. So, the opposite of that is to say that we're below 1 over C. And so more specifically, our density is bounded by 1 over C minus some increasing function, right? So if you're strictly below 1 over C, you can choose, let's say, a downward sloping linear function starting at 1 over C to bound your density. But in principle, you can be right at the critical threshold of 1 over C, and your density will be going down according to some non-trivial function psi. All right, and so if that's the case, you can prove the regularity estimate in the third line from the bottom. So the change in lambda, so the change in the losses, the change in the position of the ice process can be bounded above by this quantity on the right. So it's given in terms of some function of the square root of s minus t. And basically, so the point is, so first of all, this estimate is sharp. And the point of this estimate is that your lambda in this intermediate regime will be continuous. If your density was strictly below 1 over c, it will be Herder 1/2, so it will behave basically like the square root function. And if you're right at the critical threshold, then you can get some other dependence on s minus t. But in any case, this intermediate regime is a situation where you don't have a jump, but you're also not continuously differentiable in general. So you can have this Herder 1/2 behavior, or a Herder continuity with some other exponent. So lambda prime would be still infinite, but you don't see a jump, right? So these are the three scenarios basically, right? So either the speed of your ice is finite, or you have a jump, or the speed is infinite, but you do not have a jump. So these are the three situations that can occur. And once you can establish that, once you can analyze all these three situations, in particular as a byproduct, you get the uniqueness for this probabilistic solution. So that's our result with Francois Delarue and Sergey Nadtochiy from 2019. So we proved that this probabilistic solution is actually unique. And so we have a nice solution theory for this free boundary problem, recast probabilistically. Okay, so to wrap up, I would just want to spend 1 minute on kind of applied conclusions and 1 minute on more theoretical mathematical conclusions. So in terms of finance, the conclusions of this work are that you can analyze this large system limit. And in particular, it gives you a nice intrinsic definition of what it means to have a systemic crisis. Namely, you can speak of a systemic crisis exactly when the function lambda has a jump, right? So it means that a representative bank in your system will have a non-trivial loss at this time. So really, everybody is impacted by the crisis in a non-trivial way. And in particular, if you're a financial regulator and you want to prevent such a situation, our analysis tells you what you should look out for, right? So in the middle of the slide, you see the condition which triggers a jump. So essentially, it's written in terms of the distribution of the asset values right before the jump. And so, in practice, if you observe the asset values, so if your banks are required to report those, you can plot the corresponding histogram. And, whenever you see that this distribution approaches a situation where jump would be triggered, so when you come close to this critical threshold of 1/c and the default boundary, what you can do, you can adjust this non-core exposure level C. And it's my understanding that some countries, for example, South Korea, have intervened after the financial crisis in 2009 exactly in this way. So they limited the non-core exposure of banks by law, and that makes a lot of sense from the point of view of this model, and should indeed prevent systemic crisis. All right. And so finally, the mathematical conclusion. So I have introduced this new solution concept for one particular free boundary problem, namely the supercooled Stefan problem. But I want to emphasize that this is a much more general principle. So you can formulate this concept of solution for a wide class of free boundary problems that have singularities. And this, the hope would be to get a well-posedness, in other words, an existence and uniqueness theory for large classes of free boundary problems this way, in cases where it is unknown. So here are just a few more examples to give you some idea of the scope of the theory. So you can look at the supercooled Stefan problem with kinetic undercooling. So that's a situation where the liquid is still below its equilibrium freezing temperature, but you model, in a sense, more precisely how the freezing occurs. This solution can be also formulated for the Stefan problem for the porous medium equation, so a nonlinear version of the problem you saw before. And that shows up in particular in the so-called sharp interface limit of phase segregation models. There are various reasons to look at such free boundary problems as well. And then, of course, you can look at higher dimensions, right? So the situation where, right, you are not just modeling how the ice block was moving from right to left, but rather you have some non-trivial geometry of your crystal, your ice crystal, and it grows, say in 2 or 3 dimensions, and you want to study the interface between the ice and the water. So in that case, you can also formulate the notion of probabilistic solution. And so in ongoing work, we're kind of developing the theory and with the goal of proving existence and uniqueness for multi-dimensional versions of these free boundary problems. All right, so I'll stop here and thank you for your attention. And of course, I very much welcome questions if you have any.
Thank you very much, Misha. It was a great talk. Do we have any questions from the audience? Please unmute yourself if you have something to ask. Well, people are thinking. Let me ask a first question. You rely on a limit with the number of parts into infinity. Mm-hmm. When we're I mean, obviously it makes a lot of sense for from an analytical point of view. It just makes things work out easier. But if we think about realistic applications, say to banks, we very often we really care about just a handful of these too big to fail banks, because with the small banks, they fail all the time. It's not a systemic risk by any means. Do you think? And one obvious solution with that would be just ignore all those small banks and think of small that do matter. But is there something more clever than that?
Yeah, so basically here you had this property that somehow we were treating all banks the same. And right, as you're saying, that's not the most realistic or most useful thing to do. So what you can do, you can actually formulate a model that's much more precise, namely, which would incorporate, on the one hand, the network structure between the banks. So, the fact that these big banks that you were talking about, much more interconnected and borrowed land from many more banks than, say, a typical retail bank. So you can really formulate this model on the network. On top of that, you can study the behavior. So as long as the network is large, you can still study the behavior of so the emergence of systemic crisis in this network. And you can, in particular, just look at those that affect the big banks. So, in this network model, you can introduce different types of banks. So for example, the too big to fail, as you mentioned, some sort of intermediate banks and maybe retail banks, for example. And you can study kind of more specifically systemic crisis affecting a particular type. So in our follow-up paper with Sergey Nadtochiy, we'll look precisely at that. And so you can develop a theory in this network setting as well. So you can also formulate or understand what triggers a systemic crisis and basically tell a regulator what to look for. So essentially, there are now two quantities that play a role. So one are these distributions of asset values for the different types. So that corresponds to what we have seen here. But then there is also the network structure, which enters through a certain Perron-Frobenius eigenvalue of the network. And so when you put those two together, you can formulate a condition for a systemic crisis and give that to a regulator to monitor for.
Thank you.
Sure.
Are there any more questions? Another thing is this issue between illiquidity and insolvency. Basically, sometimes the banks are simply tolerated too many losses, and they are effective companies, and there is nothing you can do. They just lost their capital. But very often, and this is a much more interesting case, if we are thinking about systemic risk, they are simply illiquid, so they do not incur huge losses over time. Over actually relatively short term, they will be able to repay all the debts, say, all the liabilities they have, but right at this very short-term moment, they are illiquid. They do not have enough cash to pay the immediate debts. Is there a way, again, something clever for us to make a distinction in your approach?
So there is some work going in that direction. Specifically, I'm thinking about a paper by René Carmona, Jean-Pierre Fouque, and a student of Jean-Pierre, where they formulate a model sort of similar to ours, where you have a delay type equation, which somehow incorporates, so actually various delays. So on the one hand, that you don't have to repay the loan immediately, and on the other hand, that the losses do not propagate immediately through the network. So in the kind of context of this structural model that I have described, I haven't seen anyone putting sort of these delay equations together with the type of interaction that I was describing, but it's certainly an interesting direction to look into. So so from the top of my head, I'm not sure how tractable this will be, but it's certainly a reasonable direction to explore.
Yeah, thank you. Okay, one last call for additional questions. Well, okay, we are 8 minutes past our deadline with the end of the talk anyway. Misha, thank you very much again for the talk. I hope people got some taste of how difficult bank regulation is, and people won't judge our regulators as harsh as they did before. Thank you.
Thanks for having me.